sampling. Actually, the notes have material on stratified sampling. I'm going to focus on the cluster sampling here, and actually tomorrow on missing data, I'll talk a little bit about stratified sampling. But there's been a lot of interest lately in how one does inference when you have a cluster structure. And this actually covers two situations, and I'll talk about some recent theoretical work and how it applies in each case. We might have a real cluster sample where there's no time series element to the data set, but we have individual level data, say, that are that's naturally grouped into clusters. Or later on this afternoon, in talking about difference in differences methods, I'll consider more specifically the case where we have individual data within a particular group within a particular time period. And these results that I talk about now will have applications to that setup as well. So I broke this down into 4 sections. The linear model with cluster effects, and that's the fairly basic stuff, but I'll just go through it and emphasize a few points. And then in particular talking about what's been learned recently about applying these so-called cluster robust variance matrices and test statistics in cases where you don't necessarily have a large number of clusters with small group size. And then specifically talk about the case where you have a small number of groups or clusters and large group sizes, and then what happens if you have large or moderately large, both of them, and then say a little bit about nonlinear models. So in the linear model, the notation here is aimed at the case of cluster data, not panel data, but as I said, this literature certainly has implications for what happens with panel data as well. And I've mentioned several times about making inference robust when analyzing panel data. So this will formalize that to some extent, but mainly I want to focus on these more difficult cases to handle. So the setup is, again, a set of draws on Y, X, and Z, where G is the group or cluster, and M then indexes the observations within the cluster or group. And we have M sub G units, so this would be like an unbalanced panel. Cluster samples usually come with different group sizes or different cluster sizes, so certainly we need to allow that. Or this could apply to an unbalanced panel, although I will be talking tomorrow about unbalanced panels and when you can ignore the fact that they're unbalanced and so on. So for now, we're just viewing this as sampling. We have observations that come in clusters or groups. And then the explanatory variables are divided into 2 kinds. X sub G, these vary just at the group level. And then Z sub G M, these vary within group across individuals or whatever the unit is. Applied to a panel data set, M here would be the time period, and G would be the cross-section dimension. So if we start with equation 1, which is just a basic linear model for cluster data, then in order to figure out how to proceed, we need to know a couple of things. First of all, are we mainly interested in the parameters on the group level variables, or are we mainly interested in the parameters on the covariates that vary within group across individual? And depending on the answer to that, we would use different kinds of estimation methods, or at least that opens the door to different kinds of estimation methods. The other issues are going to be about the error structure. So in this error term here, do we have a so-called group or cluster effect? And if we don't, well, then things are a lot easier. So we're mainly concerned with the case where we do. And usually that's written as in equation 2, where we explicitly write the cluster or group effect C sub G, and then there are the idiosyncratic errors U sub G sub M. So G could index something like a school here, and M could index students within the school, where we might have a lot of schools and a few students, or maybe even lots of students per school. But in any case, we think of the school as the natural cluster for the students. The other issues are the regressors appropriately exogenous? Of course, that will certainly determine how we estimate the parameters. And then the key issue that's been looked at recently in theoretical literature, and certainly has been a concern for some time, is what are the relative sizes of the group and within group samples. So do we have a large number of groups and with small sizes, or is it the other way around, or is it somewhere in between? And this determines how well some of these robust procedures actually work in practice. And there's been recent theoretical work that essentially confirms what people have noticed for a while. And I'll try to summarize how that applies to both cluster samples and panel data sets for the various configurations that come up. I'm going to explicitly consider two kinds of sampling schemes. One is the easiest to deal with, and that is where you think of having a large population of clusters, and then you pull these clusters at random from the population, and then within those clusters you get individual data on individuals. So this would be a case where you're looking at a large population of schools, and you draw several hundred at random, and then within those schools you get information on lots of students or something like that. But the key is you have a lot of clusters, and so it makes sense to think of doing the asymptotic analysis as the number of clusters is getting large. So there are some other examples. There are families or firms or classrooms and so on. A different way to come up with a data set that has a similar structure is to actually think of partitioning the population into a fairly small number of groups, and then sampling within those strata or subgroups. And this leads to a data set where you have usually just a few groups, but you might have a lot of observations within each group. And of course, even though that data structure looks similar to the first kind, it matters whether you have a large number of groups or a small number of groups when you decide how to do inference. So I'll first cover the case where the inference is relatively straightforward, just to make sure we understand that if you want to try the same sort of inference on other cases, you have to be aware of what's known and what's actually not known. A fair amount is known by now, actually, so we can avoid certain pitfalls. So with large group asymptotics, as I said, the idea is we have a large number of groups G, so technically G goes off to infinity. We fix the group sizes. This is certainly the appropriate setup for panel data, where you have a large number of cross-sections and relatively few time periods for each cross-section. And it's relevant for certain kinds of cluster samples where you have lots of clusters. Okay, so how should we proceed? Well, if the covariates at both the group level and the unit-specific level, the individual level, are exogenous in the sense of 3, then we can actually just use pooled OLS, of course, by pooling across clusters and within clusters. So there's nothing new or exciting there. Under that exogeneity assumption, you get consistency and asymptotic normality again as the dimension of the groups gets large. And of course, we can estimate the parameters on both the group level variables as well as the unit specific level variables. Okay, so in the panel data case, that actually does allow for non-strictly exogenous variables. However, if we think there's this cluster effect in V sub gm, then of course we're assuming that everything is uncorrelated with the cluster effect, and that makes that comment a little less useful. But still, one does see pooled OLS applied to cluster samples, and often the reason that's done is because there is interest in the effects of the group level variables x sub g. If we, later we'll talk about so-called fixed effects in a minute, but of course we don't want to eliminate the x sub g's if those are the variables that we're actually interested in. So of course, when we do this pooled OLS estimation, whether it's on a panel data set where we've left the unobserved effect in the error term, or whether it's on a true cluster data set where we've left the cluster effect in the error term, it has the same effect of making the inference invalid unless we adjust it and allow for correlation in computing standard errors and test statistics. So we can afford to do this quite generally. This is why this is the easy case, because with a large G, we don't have to impose any structure on the correlation within a group. We simply estimate a variance matrix that allows for arbitrary correlation within cluster or within observation in the panel data case. And that pretty much takes care of things. Of course, it's not efficient to use pooled OLS usually in this case, but it's easy, and we know how to do inference that is approximately valid. So the variance matrix is this sandwich form that's given in equation 4, where again, the averaging, the right way to think about the averaging in this particular case is across the number of groups, and then we don't have to impose any structure in estimating all of the pairwise covariances and variances in the middle part of the sandwich. Okay. This is the variance matrix that's now reported rather routinely by just adding cluster with an identifier to tell you what the grouping is, and can be added onto lots of different commands, say in Stata. So this is, of course, easy to do these days. If we strengthen the exogeneity assumption to that in equation 5, so the difference here is that we're now putting the full matrix of regressors that change within group z sub g into that conditioning set. So now we're not just assuming that everything is uncorrelated with the cluster effect, but we're assuming that the regressors for one person within the cluster are not correlated with the errors for another person within the cluster. So this sort of assumption, unless it's been modeled directly, would rule out things like peer effects and so on, where you might allow that somebody's x's, or in this case I should say somebody's z's, actually affect the outcome of a different person. There are ways to model that, of course, but at this particular level, we're not accounting for that. So if this is true, if this assumption is true, then we can do something else. Of course, we can do a GLS type procedure, which generally will be more efficient than doing pooled OLS. And the most common thing to do would be to specify a so-called random effect structure. And this is, of course, in general, a random effect structure on an unbalanced data set, because we don't want to assume that the cluster sizes are the same. So the variance matrix in the case of where we actually take the cluster setup seriously is given in 6. So that would mean that we're assuming the idiosyncratic errors are uncorrelated within a cluster, that we have common variances within a cluster, and then the sigma squared sub c is actually the variance of the cluster effect. So with that particular structure, of course, the so-called random effects estimator suggests itself, there's the, one should always be aware that even if you believe in this particular structure of the composite error, so if I go back up to equation 2, even if we believe this structure where the U's are uncorrelated with the cluster effects, we have constant variances of the U's, there's always an assumption that those variances don't depend on the regressors. So it's not just enough, of course, to assume that the unconditional variance is given as in equation 6. We also need to assume that that is the conditional variance if we're going to use the usual random effects inference. So in other words, if we're going to estimate random effects and then use the standard errors and test statistics that are reported as a default, then we have to assume that the so-called system homoscedasticity assumption, which means that the conditional variance is equal to the unconditional variance, and in addition, that the unconditional variance has the structure in 6. Okay. So if that's not true, well, there it is right there, equation 7. That's the so-called, and of course, even if we relaxed the random effects structure and did a GLS analysis that was unrestricted, say in a panel data case, you still are assuming 7 if in fact you're using the usual inference. So again, the random effects estimator has well-known properties as the number of groups gets large and the group sizes are fixed. It's root G asymptotically normal, and inference is straightforward. Now, one point that is sometimes overlooked is that there are good reasons to make the inference fully robust even if you've done random effects. This is especially true in panel data because, of course, the idiosyncratic errors could be correlated over time, and the usual random effects assumptions don't allow that. So even if we're doing random effects as a way of accounting for the serial correlation to some extent, but might want our inference to be more robust, then we can compute a fully robust variance matrix that doesn't take the random effects assumption seriously. This, by the way, is with cluster samples where it doesn't make any sense to talk about serial correlation in the idiosyncratic errors. It's, I think, the case for robust inference is a little more subtle, but there is a case to be made. So if we start with equation 8, for example, which is similar to some models we talked about before, it's a random coefficient model where the coefficients vary at the group level. So this is the random coefficient right there, gamma sub g, where I now am violating the convention I mentioned before when I said that Greek letters would always represent parameters to estimate. So this is now a random variable, okay, that is not to be estimated. But it has a mean that we would hope to estimate. And so if we then plug in its mean, which I've called gamma, then see, the idea is we have a large number of groups. We're not necessarily going to try to estimate these gammas for each group, but we hope to estimate something, which would be the mean of them. Then in effect, what happens is this gets put into the error term, and the presence of that would generally cause correlation within cluster, and correlation that depends on the regressors. And so this is a random coefficient model where you actually ignore the fact that the coefficients are random, go ahead and apply random effects or some other GLS method that it makes sense to then to make the inference fully robust, because the system homoscedasticity assumption certainly fails in this particular case. Now, it may be a minor problem, but it doesn't hurt with large G to at least compute them and to see whether it makes much of a difference. Okay, with of course, one way to handle group effects or cluster effects is to get rid of them. We already talked about this in the panel data case. And this is a good idea when we're really interested in the coefficients on the individual specific variables. Then the easiest thing to do is to remove the cluster effects. Of course, that allows those to be arbitrarily correlated with these covariates, and so it affords us some robustness in inferring some sort of causality in these estimates. So differencing out the cluster effect. So this is now a within group demeaning that we're doing, and that leaves the, of course, that takes the cluster effect or the group effect out of the error term, and then we just apply pooled OLS to this equation. So again, this is a case where certainly with panel data, it's pretty obvious that you might want to make the inference fully robust. With cluster sampling, it's a little less obvious that that's true, but again, there are cases, and I'll bring back this random coefficient, this random slope case, where we already saw in the second lecture how fixed effects could actually still be consistently estimating the average effect gamma, but in fact, even if it does consistently estimate that, it leaves this term here in the error term. So even for cluster samples where we would normally assume that the idiosyncratic errors are independent or at least uncorrelated within cluster, this sort of neglected heterogeneity could also cause that to be untrue. Like I said, these days, of course, doing the robust inference is a very standard thing to do, and the main point here is it may make sense to make it robust even for a pure cluster sample. Okay, and there's the formula, just so. It's the same formula as before, except there are no x's, so these are now just the z's, and they've had the within group averages taken out, and then those u sub g hats are the so-called fixed effects residuals. Okay, now, that's, as I said, the case for doing this with a large number of groups and small group sizes is fairly clear, I think. The more interesting case is what happens if you don't have a large number of groups and you may have kind of large group sizes. It doesn't, just because the original theory was worked out for the large G case, doesn't mean that applying these formulas to other cases is a bad thing. But, we should have some justification for doing that. And there certainly was simulation evidence that suggested that these work reasonably well in the case where you have reasonably large group sizes as long as you also had a reasonably large number of groups. Now, it depends a little bit, well, it depends a lot actually, on whether you take out the group effect or not. So I'm going to summarize some work that recently that formalizes what I think we pretty much had good intuition about in some simulation evidence, but it's useful to actually summarize the theoretical results. So the question is, should we use the large G formulas with large M, where large, of course, is always a matter of interpretation because we don't really know in any particular application how large these dimensions have to be in order for the results to kick in. So Chris Hansen has written two papers recently. We'll talk about the second paper later on when we talk about difference in differences. The first paper basically looked at this issue about what happens when we have these various configurations with G and the M sub Gs. And so I'll just summarize what comes out of that work. So it actually makes a difference, certainly not for the theory, but I think in understanding what are the practical implications of his results to separate out the real cluster sampling case from the panel data case. because, of course, with panel data, there's this notion that you could have serial correlation, that because of the time ordering, it makes sense to talk about that correlation dying out as you get farther and farther away in time. And with cluster sampling, that doesn't make as much sense. So first consider the so-called true cluster samples. He has a theorem that says, in effect, that if you let G and M sub G both get large at the same time, then the inference that's based on those matrices, that matrix that I wrote down for the pooled OLS estimator, is valid even if there's arbitrary correlation within group. Okay, I should say, this is all based on the assumption that there's independence across groups. Okay, so the question is, what about the dependence within a group? And with a cluster effect, there is a lot of dependence within the group when you leave that in the error term. Okay, so, but the results are for the case where there's independence across the groups. That in a panel data, that would mean independence in the cross-section dimension. Okay, so the usual inference that's based on the fully robust variance is valid even if there's arbitrary correlation within the groups. So that means that even if you have pretty big group sizes, as long as you have a fairly large number of them, then you're on pretty safe ground in terms of getting appropriate inference, at least that has the right size asymptotically. So, if you had 100 schools and 100 students per school, you might say, well, can I really appeal to this theory that is based on a large number of groups with small group sizes? His results say basically the answer is yes. And this is important because in these applications, you're often interested in the effects of school-level variables like spending per student or something like that. And so you can't use a fixed effects transformation to eliminate the school effect, because it eliminates the variable you're interested in as well. So that, as I said here, you probably in these kinds of examples, you're leaving the school effects in the error term because you're interested in a school-level variable. Okay, the bad news is that his results don't apply to the case where G is small and the group sizes are large. And this, we'll actually discuss what has been proposed in this case. But this is the case that doesn't follow from his work. So if you have a small number of groups and they're somewhat large, and you try to make the inference fully robust to arbitrary correlation within the groups, you shouldn't expect it to work very well, because you're trying to basically estimate a lot of correlations with a few number of group observations. Okay. Now, of course, he has some simulation evidence that shows, well, maybe it's not so bad, but it's also true that if G is really small, a handful, and the group sizes, are 30 or so, then it's not going to work so well. So we shouldn't expect this to work very well, and his results don't apply to this case. And so we'll talk about what to do. Now, that's assuming that we've done pooled OLS. Okay, so that we've left the cluster or the group effect in the error term, and then we can't expect that to do well. Of course, if we take out that cluster effect, then we've now greatly reduced the correlation in the within groups in the errors. And in fact, in some sense, it makes sense to just assume the correlation is zero. So if we do so-called fixed effects and we have just a small number of groups, well, in his setup, you can pretty much just treat the estimates of the cluster or group effects, in this case, as estimated parameters, different intercepts we're estimating for each group, because we only have a few groups, or a small number of groups, and we have a lot of observations per group, and so we can estimate those things fairly precisely. So if you take that point of view in the context of his results, as it turns out, he does have results that show a certain kind of inference is valid in that case. It's not as general as his other results, and so there are some restrictions. But you can do something, and that is you can essentially adjust the degrees of freedom in the t distribution that you use, and actually you also have to do an adjustment to the robust variance matrix estimator also. So if you use the fully robust cluster variance matrix after having taken out the group effect, and you do it, I don't know, for one of those reasons I mentioned, because you might think there was a random coefficient that you omitted, but it turns out that it's not, then you pay a price for being conservative in this way. And the price you pay is you basically have to use a t-distribution with g-1 degrees of freedom to do inference. Okay, so if you had 5 groups, now you have to compare your t-statistics to a t with 4 degrees of freedom. Instead of, well, what we would normally do is you would use a standard normal distribution, because you'd be assuming the asymptotics are working for you in the large number of groups. So the reason I say you pay a big price for that is because if you didn't compute the robust variance matrix estimator, and you really do have independence once you take out the cluster effect, then in fact all you'd have to do is make your inference robust at most to heteroscedasticity, and then you could use large sample asymptotics because the group sizes m sub g are large. Okay, so I probably didn't say that especially well, but if you take out the cluster effect by basically treating them as parameters and estimating them, then you have data that are independent. Okay, they're not identically distributed, but that doesn't matter for applying these large sample results. So under that scenario, then you should be legitimately able to use large sample analysis where the number of observations is large because the group sizes are large. If you say, but I'm nervous about this and I'm going to use these robust variance matrices anyway, then his results show that you have to use a t-distribution with g-1 degrees of freedom, even though the underlying data are actually independent. Okay? So there is a cost to doing that, and it's basically that. By the way, this multiplication by g over g-1 to that formula that I had way back where, that, as it turns out, packages like Stata do that correction automatically anyway. So that part of it, you don't have to actually be, you don't have any extra work to do, but certainly using the t-distribution with a small number of degrees of freedom is, oops, where did that go? Yes, is the thing that costs you in terms of the certainly confidence intervals if you use that distribution to construct them. Okay, so notice that the G here is fixed in his asymptotic analysis, okay, and it's done with the number of group observations going to infinity. Okay. So what about panel data applications? Just quickly, so the results that I mentioned for the cluster case suggest that the fully robust or the cluster robust inference should work well when the cross-section and time series dimensions are similar and not too small. So you can do pooled OLS and leave the so-called unobserved effect in the error term. So that's very similar to the cluster effect case. If you have extra serial correlation, okay, so there's this somewhat subtle point though, and that is if you're going to do the common thing though, and in addition to so-called fixed effects in the cross-section, you allow time effects, okay, now you have to have both a large cross-section and a large time series, and you have to assume that any serial correlation that's left over is of the weakly dependent kind, so that it's dying out as you get farther and farther apart in time. Okay, yeah, so I guess that's all there is to say. So if you're in the standard case where you want to control for aggregate time effects as well as fixed cross-sectional fixed effects, then his results apply as long as you have, a reasonably large size of n and t, and you don't have, you don't have unit roots left over after you've taken those things out, basically. And then there are simulation results that basically verify. Some of the simulation results came before his theoretical work, and the Bertrand et al. Paper that showed that these things work reasonably well as long as you have a reasonable number of cross-section observations to, and in that case you have weak dependence across time. Okay, so what happens if we have a small number of groups and large group sizes, and we're interested in doing inference on the covariates that change only at the group level? Okay, because as I said, if we're interested in doing inference on the covariates that vary within group, then the easiest thing to do is just to estimate the group effects and go from there. Okay, well, the news is not good depending on how you look at it. Donald and Lang recently considered this problem. Actually, the paper was recently published. They considered it actually several years ago. And this is related to the so-called Molten problem, from how does one do proper inference in the presence of cluster samples. Donald and Lang were really focused on the case where you really have a small number of groups, so just a handful or even a couple. And they set the problem up so that you have this unobserved group effect, just as in the model we talked about. So I'm going to consider first the very simple case where you just have, let's just say, a single covariate. It might be a policy variable, 0, 1 variable. And you have a cluster effect, and the question is, how can one do inference in this setup? Well, so that's in equation 11, right there. And you can write that in two ways. You can think of that as there being this cluster effect C sub g, which you don't observe. Another way to think about it is that there's this cluster or group-specific intercept. Okay, so even if you assume that the cluster effect is independent of the x's, okay, it's difficult to do inference in this setup because we only have a small number of groups. So as I just mentioned, since we can't take away the cluster effect by estimating them or doing the within transformation, we are leaving that cluster effect as part of the error term. As I just mentioned, the standard errors don't work in that particular case, and we shouldn't expect them to. So what did Donald and Lang propose to do? Well, in this particular case, let's actually consider, well, we don't have to consider the case of the same group sizes, but, well, okay, so let's just consider the case where the group sizes actually, okay, they don't have to be the same. There is a result that requires them to be the same, but not the basic problem. So they actually recommend studying the problem using the regression in 13, which is to take the group averages. So there's only one thing that varies within group in this case, and that's the response variable. Okay, the x only varies across group, and the response variable varies within group. So in this case, the solution is to basically just use this regression where you regress the averages, the group averages on, well, in this case, a constant and a single covariate. Okay, now, you can see what the issue is here, because the x's, because they're exogenous, you can just condition on them. If you write down the equation in terms of the average y's, you can see that they're getting their distribution from the average of these composite errors. But the composite error depends on this unobserved cluster effect. With large group sizes, the extra effect that's coming from that idiosyncratic error is actually usually insignificant relative to the variance of the cluster effect. And so the contribution, if you will, from adding more observations within cluster is really just in how it changes the mean of y. It doesn't really add new additional information. And in fact, this is exactly the same estimate. This is where the balanced, the same number of groups comes into play. This is identical to the OLS estimate where you pool across both groups and within groups and just do OLS. This is the same thing as regressing the averages just on this intercept and the single explanatory variable. So it's not as if it's a different estimation method, really. It's just how one is actually going to go about inference. So how can one do inference in this case? Well, remember, the problem is that G here is kind of small. Well, you can only do inference if you add some fairly strong assumptions. And the main assumption, the most important assumption, is that the cluster effect has a normal distribution. Okay, so that's given by this at the top. So it's independent of x, and it has a normal distribution. Okay, once we have that, then we can decide whether we want to do approximate inference or exact inference. In the case, if we want to do exact inference, then we can assume that the individual specific errors are also normally distributed, but we would also have to assume that they have the same, that the group sizes are the same. So in that case, this averaged error here, where that would have this normal distribution, and because the group sizes are the same, the normal it's a homoscedastic normal distribution. And then, of course, that means that this model written down in 14 is a classical linear regression model. Okay, so that's basically the solution, is to treat this as a classical linear regression model. Now, you can see that this is very costly because if G is something like 5, again, or 3, then you're doing inference with a t distribution with a very small number of degrees of freedom. And by the way, that if you, again, changing the assumption that that is different across groups, basically what you're doing then is just saying that you're going to ignore the contribution to the idiosyncratic errors and just assume that it's large enough so that the average is normal, and you're going to ignore the heteroscedasticity that it implies. So if you think about this, this is quite different from what you would do if you ignored the cluster sampling. And it's more than just not computing cluster robust standard errors, because there you would do it and then you would use the wrong degrees of freedom in the t distribution anyway. This is a matter of using G minus 2 in the t distribution, okay, which again is going to give you very wide confidence intervals compared with what you would get if you used, say, the standard normal approximation. So the question is this the solution to this problem? Well, it certainly is a solution, and if you really like to be conservative, then it's, I guess, the way to go. If you this can be extended to the general model, so if you allow x to be a vector and you allow some individual specific covariates, then basically you're back to estimating the so-called between regression, where you just use group level averages and then you treat this as a classical linear regression model. Unfortunately, of course, in this case, you're going to need the number of groups to be at least as large, to be bigger than the number of parameters that you're trying to estimate in this equation. So But if you have that, then you can carry out inference. And there are applications where you might have G equals 50 states or 30 regions or something like that, and you're trying to do this with a fair number of right-hand side variables. And then this just says that you should be, you shouldn't use asymptotic analysis. You should use finite sample analysis in doing this, even though, of course, it requires normality and everything. And this is not this strategy is not uncommon by any stretch. People often just do this as a way to check the results using the individual level data. The question is, how are you going to do inference? And Donald and Lang suggest, well, you do inference with an exact t distribution, or at least an approximate t. Now, I do want to point something out here. I think this observation is a really good one, but it does also have the implication that it basically rules out some staples that were taught way back in introductory statistics for doing policy analysis. In particular, if you have two groups, Donald and Lang's setup implies that you can't do inference. Okay, that if you so suppose you just have two groups and you've collected a large number of observations within each group, what would the Donald and Lang estimator be in this case? It would be the difference in means that we would compute from a basic statistics course, right? Of course, there, if you do a comparison of means, you would be left with doing, inference probably based on the standard normal distribution, because, you have groups of a couple of hundred each or something like that, or even maybe as low as 50 or 30, and so then you would say, what's the approximate distribution of this difference in means? Well, it's approximately normal, and you can estimate the variance. So in the Donald and Lang framework, their estimate would exactly be the difference in means, but you'd have 0 degrees of freedom, so you couldn't do any statistical inference. So, and in fact, any time you basically have parameters that are just identified in this setting, you can't do inference. And so this, as we're going to see later on this afternoon, this in this typical difference in differences setup, it basically says you can't do inference if you are worried about this kind of cluster structure. So one wonders whether you should just assume that you can't use a comparison of means to study the outcome of what might be a pretty good randomized experiment. Okay, I don't know. I mean, if you took two schools and you had sampled lots of students per school, and there was some intervention at one school, then it seems like you should be able to do to compute a change in means in some test score or something like that, and then do a simple t-test on the difference as a test of whether the policy had an effect. So, I'm still not entirely sold that we should just throw that sort of thing out. Even in the case where you can do this analysis, so just as an example, if you suppose you had 4 groups, but you were still back in this case where you just had a single policy indicator, and let's suppose 2 of the groups are control and 2 of the groups are treatment, then what Donald and Lang would say would be to run a regression of the averages on this indicator using the 4 observations that you have, and then using a t with 2 degrees of freedom to do your inference. Again, the estimate is quite familiar. What would the estimate be in that case? It would be this. It would say to average the 2 outcomes for the treatment group and subtract off the average for the control group. And of course, if you had lots of observations within each group, each of the 4 groups, you might think that beta hat has an approximate normal distribution. Okay, but that's not what would happen in this case. You would use a t distribution with 2 degrees of freedom in the Donald and Lang setup. So basically, the reason that comes about is because it may be that the means within each group are not the same. Okay, and that would be the role of adding this C sub g term basically onto the end of this equation, is that mu1 and mu2 might not be the same, and mu3 and mu4 might not be the same also. But should we necessarily reject 16 as as having an approximate, normal distribution because of that. Well, I don't quite have the complete answer for that, actually. Okay, another possibility then is essentially what happens in this example where you have 4 groups, but 2 are treatment and 2 are control, is that implicitly, in some ways, the restriction is being imposed that mu1 and mu2 are the same, and mu3 and mu4 are the same. And if you were to impose that restriction and use a minimum distance procedure, you would exactly get the estimates that I wrote down. Okay, so one way to view this problem is that restrictions are being imposed on parameters, and of course those are testable restrictions if you choose to test them. On the other hand, you might choose to not care about whether those means are the same and just say, I'm going to define essentially the treatment effect as being the population analog of this thing right here. Okay, it's hard to, if you did this to 2 schools treatment and 2 schools control, sure, this might not be the right weighted average to use in terms of what the best estimate of the effect on the average gain is, but it's not clear you want to just say, I can't tell whether that's significant because I have to use a t-distribution with 2 degrees of freedom. But there are differences of opinions on this particular point. So the notes talk about how this can be done in a minimum distance framework. The general issue is, though, and this has been used by, I have one reference here, Loeb and Bound, when they had 36 groups, and then basically they treat these parameters, actually they had group-specific slopes as well. And the idea is to think of these x's, these group-level variables, as imposing restrictions on the parameters in this model. So the idea is, with a large number of groups, you can estimate these things fairly precisely, and then basically you can test whether these restrictions are satisfied. Now these are restrictions on just the intercepts, which is the common case, but you can do it for the slopes as well. So if you set this up as a minimum distance problem, then the estimation is straightforward because you just estimate these intercepts and slopes within each group, and then you can impose the restrictions using the efficient minimum distance estimator, and then test the restrictions that are being imposed. Of course, if you reject those restrictions, you may actually wind up back using the Donald and Lang approach if you are worried about those restrictions being true. And it's justified because, in effect, you can ignore the estimation error in the parameters that you've generated using the within-group regressions. So in other words, if we have large group sizes, then you treat these estimated intercepts as if roughly they're basically the true intercepts. And this is the term, if it really is there, which is going to dominate anyway. So you can now just analyze this equation 20 as if, again, it's a classical linear regression model, at least under the assumption that this thing has a normal distribution. So this is a procedure that is fairly widely applicable. And if G is not too small, then this is likely to give very acceptable estimates. And then you don't have to really worry about why these intercepts are different across the groups, as long as, of course, you're willing to assume the deviation here is uncorrelated with the policy variable x sub g, okay, which, of course, you might question, certainly in general, but if it's a good randomized experiment, perhaps not. So it looks like the last thing I can actually say is what happens if the group sizes are both large. Well, there we have more flexibility, because in addition to ignoring the first stage estimation error in delta g hat, okay, which I argued that we can do when the group sizes are large. Now in the second step, where we have this equation here, well, if we have if G is large, then we can apply the central limit theorem and don't have to assume that this cluster or group effect has a normal distribution. So you can, if you have a large G and large group sizes, then of course that should be better than having only one of them large, and that comes from the fact that as G is large, it's not going to matter if we use the T distribution there, right? And it's also going to be robust to, well, heteroscedasticity and non-normality in the group effects. In fact, there's one version of this method in that Berry, Levinson, and Pecos have suggested for analyzing structural models of markets. And one of their procedures is to, I guess I mentioned this later on under nonlinear models, but since I'm going to have to stop, I'll mention it now. One of their procedures is to basically estimate models like multinomial choice models on individual level data. Then there are estimated intercepts, and then in a second step, those are modeled as functions of either product characteristics or market characteristics. And in effect, if you have a large number of individuals to estimate these deltas, the delta hats, then in the second stage, you can more or less ignore the estimation error that is obtained in the first stage. The one important difference in what they do and this is that they actually are worried about correlation between this unobserved market effect or product effect and these attributes, which include things like prices. And so in their second stage, they use an instrumental variables type procedure. But it's justified in this kind of setting because you don't have to assume normality here. Okay, so we can use large G asymptotics, and then we can ignore the fact that we estimated the deltas in the first stage. Okay, now their analysis is much more sophisticated because they actually have a full formula for accounting for the first step estimation as well as the second step, as well as simulation error that comes about because the first step estimation often requires simulation methods. But as they noted that usually this particular error in estimating the delta G's can be pretty much ignored because it's swamped by everything else later on, either the simulation error or the variation in these unobserved market or product attributes across G. Okay, so I will not be able to cover nonlinear models, I guess, but the comments are actually very similar, and you can do very similar things using these two-step methods because, well, actually the Berry, Levinson, Pecos stuff is an example of that, in fact. Okay. Questions? Yes?
So when you're going through, there's a lot of large G and small G. When you go back through the notes, can you tell us what the minimum large G is? I know it changes from spot to spot. Like, for example, how big is large G at this point?
You really want me to go on record throwing out some number?
So when the referee comes back on the
well, okay, let me try to dodge that a little bit, but suppose we're thinking of this as a regression model, and suppose that we just have two parameters to estimate. Okay, so let's actually act as if we really do have a large number of individuals. Okay, and so the first stage estimation can be ignored. Well, when do we feel this is a simple bivariate regression? So when do we feel comfortable saying normality is not critical in that case? 30 observations? 50? Of course, it hinges critically on what the distribution of this is. Is it heteroscedastic? Is it close to normal, and so it's the usual inference is going to be okay? once cap G starts getting up to 50 or 60 or so, then you don't even really make a distinction between the t and the normal so much, right? So I don't know. 50, let's say 50.